Okay, so let's start with our first theoretical result, and this may seem a little bit abstract, but you'll see soon enough how this lets us be able to determine when a state is recurrent. So let's see, we're going to start off with this definition here, right? So what I'm going to be doing is summing up a bunch of indicator random variables right here, right? So this is an indicator random variable that the chain at time k is in state y. So if this is true, right, we put a 1, and otherwise it's a 0. And if you sum these over k equals 1 to n, you're essentially counting the number of visits to state y in the first n time steps. That's all this is, right? So big N script ny is the total number of visits in the first n times steps to state y. And then, we see infinity again here, right? So this is going to be the total number of visits to y in all time, right? The number of visits to state y to ever happen, right? In all of possible time, right? Y is, again, bigger than any natural number, and that's what we've set here. It amounts to taking a limit of this expression as n goes to infinity. That's what this represents. So why is this useful? Well, first we're going to try to compute its expected value, and you'll see in a second what this means for recurrence. So we're going to be computing on this left-hand side the expected number of visits in all time to state y when starting from state x, and the claim is going to be that it's equal to this ratio here, with a rho xy is a slight generalization of our notation so far. Rho xy is the probability of reaching state y from state x in finite time. Right? So this represents our hitting time of state y, right? The smallest amount, the first time that we hit y, that's what ty is. And here, right, we're looking for the probability of whether we can reach y in finite time starting from x. So again, rho xy is the probability that we reach y from x in finite time. And just to compare this, you see that rho x was for us the probability that we return in finite time to x. And so this is just a slight generalization where instead of returning, we're gonna start at some state x and reach another state y. And then, consequently, rho yy is nothing other than rho y in the notation of that screenshot. And moreover, you'll see that when y is recurrent, rho yy equal to rho y is equal to 1, so we get a division by 0, which hopefully potentially brings this up to infinity, meaning that when y is a recurrent state, the number of visits to it, expected visits to it, is infinite. And you have to be a little bit careful here. So here I was a little bit brief on what happens if we divide 0 by 0, and so here I clear this up. This rho xy here, when this is 0, the expected number is 0, and here we don't even need any kind of proof. This is obvious why this should be true. So what does this say? This is saying that the probability of reaching y from x in a finite number of steps is 0. Well, if we can't reach y starting from x in a finite number of steps, we never visit y. And so, no doubt, not only is the expected value of ny 0, and ny is 0 in that case as a random variable, right? No longer random, really. If you can't reach y, don't expect any number of visits. Now, when there is a possibility of reaching y, that's what this clause is for, then you do get this expression. And here, again, when y is recurrent, you'll divide by 0, getting infinity, so you're expecting then an infinite number of visits. So right now, hopefully this all seems correct, but maybe you're wondering what's the point. I will get there, and I'll basically show you not in the next clip, but in the clip right from then, maybe even in the next clip. I'll try to squeeze it in the next clip then. Why this is useful, and how this lets us determine when a state is recurrent, and we'll see examples of this in the next lecture worked out in full detail as well. So I think now, hopefully you see the statement of the theorem and kind of the setup for it. Let's dig through the proof. I'll give you kind of the broad ideas, and there are some things that I just don't have enough board space for here, so I'll leave them till the next clip. And in particular, this very first statement, which if you look at it, it may seem kind of striking, or maybe you've seen it. This, in fact, is a true statement, not just for the variable ny, but for any discrete non-negative random variable. And so that's why I'd like to leave this as a separate proof. This is based on Fubini's theorem. Essentially, it amounts to the exchange of a sum and an expectation, and I'll leave it. So hopefully, believe me for now that this is true. And in the next clip, if you're curious, I'll give you an even more general result, which hopefully will be useful for you elsewhere. But for now, let's take this first identity as true, even though it may seem kind of mysterious. The more important one is this equality here, that we kind of can sketch out why this is. But first, we'll need to define what's on the right-hand side, and specifically, it's these times tky's. So what I'm doing here is I'm generalizing the notion of a hitting time, and I'm doing it in a recursive fashion. So let's start off with ty 0 as being set to 0, so not even random. What is t1 then? T1 matches our definition of a hitting time. It is the first time after 0 that we reach state y, right? So t1, like I've written here, matches our previous notation of ty, right? Or rather tx, as I've written here. It's the same exact definition, only with y replacing x, but that's just that's arbitrary. So now that we have t0, we have t1, we understand what those are. What is t2? Well, t2 is going to be the first time that we return to y again after leaving y, right? We've already hit y, and now we're going to add on to this trip the first time that we hit y after already hitting y on the previous trip. So I've drawn this out in a little bit of a diagram to maybe help you kind of visualize this. Let's say this is state x, this is state y. The length of time that it takes me to go from x to y is exactly what t1y denotes, right? This guy right here, the very first hitting time. So the length of this trip, right, from x to y, this line here, the length of the length of this trip, meaning the number of time steps it took for this trip, that's t1y. Now, once we're at y, the chain is going to leave and go all the way around, and potentially, right, maybe and maybe not, but suppose it reaches y again, the length of that total trip is going to be denoted t2y. So by total, I mean starting from x, including this trip, and including this trip on top of it. That's t2. And then finally, t3, not finally, but in the next, obviously, in this step in this recursion, is to define t3y. That's going to tack on an additional length of time that it took to go make another loop, and leaving y and returning to y again, right? So it's important that I'm kind of accumulating time over and over, right? This is the it's this if you kind of parse this definition carefully, you'll see that these tyks are increasing with k, right? Anytime I increase k, these random variables are going to get larger and larger, or longer and longer, because they're measuring time. And just to sum up, again, one sentence, what is tky? Tky is the total trip, the total length of the trip taken, right, to visit state y k times, right? Tky is the total number of time steps that it took to visit y precisely k times, right? And so precisely is important here, right? If you see in this kind of trip decomposition, I moved from x to y to visit it once. I've moved over here to visit it twice, and then I moved here to visit it 3 times, right? And so that's why T2 and T3 are accurate. It's an accurate notation there. So hopefully, you've digested what this tky variable is. Why is this true? Well, this is not only true in terms of probabilities, it's true in terms of sets. So you can actually argue that these two sets are equal, not just their probabilities. So that's actually a difference, right? So this is an even stronger statement. And to prove this, you usually want to kind of argue from left to right and then right to left. So, we can, for example, assume that this is true and then show that this is true. And then we can assume that this is true and show that is true. So let's start with, this left-hand side. What's the left-hand side saying? It's an event, right? It's, describing some sort of event. What's the event? It's telling us that the total number of times steps to visit y precisely k times is finite, right? We took a finite number of steps to visit y k times. Well, what does that tell us about the total number of visits to state y? It had to be at least k, right? If in finite time we visited y k times, then the total number of visits in all of time has to be at least, k. Maybe, after, the kth visit we've ventured off and never returned to y. That's fine. In that case, n infinity y is equal to k. But, here you have to say greater than k because, all we have information about it on this side is the fact that in finite time we visited y precisely k times. Not more, not less. And possibly, and then obviously in all time, right, that leads to the conclusion that we had to visit it at least k and possibly more, right? The key difference is that here you have sort of all time, infinite time to make your visits. Okay, so now, you can go the other way, right, and start off with saying if in all possible time we've visited y at least k times, what does this say? What does this tell us about the time that it took to visit y k times? Well, it had to be finite, right? Because if it wasn't finite, this would have to be less than k, right? If it took us an infinite amount of time to visit y k times, right, then in all of time we wouldn't have been able to accumulate k visits. So hopefully I've convinced you, right? You can kind of think on your own, and the key point here is that when you want to establish an equality between two events or two sets, you want to conduct a proof going this way and that way, right? Given this, right, and this is essentially, an even more rigorous way to write this would be to take an omega, right, an outcome in this set, and argue that it's also in this set, and then conversely to start with an omega in this set and argue that it is in fact in that set. And so here they turn out to be equal, and that justifies replacing every probability, right, in this sum by this probability. And then the final step that we want to argue is the equality of these two, right? So the equality of this probability, writing it as this product here. So maybe let's take a break from that side and let's start off here, right? So what's what's here? First comes the probability that we've reached y from x in a finite amount of time, and it's multiplied by returning to y in a finite number of steps k minus 1 times, right? This is, right, if these trips are independent, and this is something that it's not the easiest thing to justify, but it is very intuitive. So in the next clip I'll talk a little bit about the strong Markov property that's giving you this independence here, and the independence here has to do with the fact that these trips are intuitively, right, you can kind of see that there's no dependence between them. The time that it took me to go from x to y should be independent, and this is because of the Markov property, right? But it's something stronger at work here, really. It's called the strong Markov property, and I'll make this clear in the next clip. But the time steps, the steps that it took me to go from x to y, are clearly going to be independent of the number of time steps that it took me to return to y on the next trip, and then that should be independent of on the next return trip, right? Why should the number of steps in this kind of round trip be somehow dependent on the number of trips in this round trip, right? There's no, once you finish it, that's it. The Markov chain forgets the past and moves on. And so, this is quite intuitive, but, it does hinge on a really important result called the strong Markov property that I'll explain in the next clip. But back here, right, if this is the probability that we visit y k times in a finite amount of time, then, we kind of, here we're explaining it or dissecting the strip in the only way that it could have happened. From x, we had to reach y to get one count of 1, right? And then we had to make k minus 1 further return trips to accumulate k total visits, right? So this part accounted for 1 visit, and this part is a product of k minus 1 independent return trips, right? This one starting from this one, then that one, and k minus 1 of them. And once you get that first trip from x to y, and then the k minus 1 subsequent return trips to y, and provided that all these trips are independent, which intuitively they are, you can write it as a product of these probabilities. So the probability that visiting y k times is finite is equal to the probability that the product of these trips of the product of these the product of the probability of these separate trips being finite is finite. Oh, so my God. So hopefully not the easiest thing to kind of say in words, but I think I've done my best here, and it's maybe up to you now to kind of think through this and kind of try to follow along, and hopefully I've been convincing. The last step is maybe the easiest one of all, right? If rho xy is 0, it doesn't matter how many things I have in the sum. It's a countable sum, and 0 times even anything, regardless of what this is, I'm going to pick up at 0. And when this is greater than 0, I'm just going to take it out of the sum, and the remainder is geometric, and that's just equal to 1 minus rho yy, right? So I think that that wraps up at least an overview of this proof. And then the next clip, I'll try to show you 3 things. One is what this all means, why it's important, how it's useful for showing that a state is recurrent, this mysterious equality, which is very useful. I'll show it to you for a general discrete random variable that's non-negative. And what's the third thing? The third thing is the strong Markov property that lets you conclude that these separate trips are indeed independent. And it's kind of like the Markov property, but you'll see the difference. The difference has to do with the fact that we're splitting it over lengths of time that are random and not deterministic. In any case, I'll stop here.